Controlled environment plant production engineering technology education modules are developed and presented by The Ohio State University, Rutgers, the State University of New Jersey, and the University of Arizona, with support from USDA NEFA through their Higher Education Challenge Grant program. In this module, we'll discuss the topic of dehumidification methods. This module is presented by Luke Power of The Ohio State University and Dr. Peter Ling of The Ohio State University. By the end of this module, you will be able to, first, describe factors affecting the efficiency of vent and heat dehumidification, describe how alternatives to vent and heat work, and identify factors that determine the ideal dehumidification method. Plant transpiration and evaporation of excess water creates high humidity in the greenhouse. Humidity management is high priority in greenhouse plant production and has become more necessary in recent years. Older greenhouses naturally purged moisture through air leaks and by forming condensate on poorly insulated cold glazing. This condensate on the greenhouse glazing could then be drained away. Newer greenhouses with fewer air leaks and higher R-value glazing hold humidity. High greenhouse humidity is problematic. Condensation can form on glazing and leaf surfaces. Condensation on glazing can block light. Water droplets that are not properly drained can splash on plants below and spread bacterial disease. Condensation on leaf surfaces can cause disease by promoting fungal spore germination. As air becomes more saturated with water vapor, it does not accept additional water as easily. It becomes difficult for plants to transpire. Transpiration is essential for cooling and nutrient uptake. Problems associated with high humidity are discussed in further detail in the humidity management modules. Let's describe the costs associated with the vent and heat method. Vent and heat is the conventional means of dehumidification. In this method, the greenhouse is opened and moist greenhouse air is vented out of the greenhouse. The vented air is replaced by relatively dry outside air. During the heating season, outside air is colder than the greenhouse set point and must be heated. The problem with this method of dehumidification is the high cost of heating the new air. Studies by Campen, Adams, and Dehumidifiers have shown vent and heat operations can make up 5 to 30% of an energy bill, with values near 20% most frequently reported. As reported on the previous slide, the cost of vent and heat operation varies. On this slide, we will discuss what factors affect the cost of a vent and heat operation. The first factor is outdoor temperature. The studies on the previous slide took place between latitudes of 46 degrees and 53 degrees north. As latitude decreases and heating season air becomes warmer, the vent and heat contribution to the energy bill will decrease. As latitude increases and the heating season air becomes colder, that percentage can be expected to grow. The second factor is outdoor humidity. When outdoor humidity is low, a minimal amount of air mass exchange effectively reduces the greenhouse humidity. Thus, less cold air mass needs to be heated, and the costs of vent and heat will drop. On the other hand, when outside humidity is higher, more cold air mass must be heated, and the costs of vent and heat will increase. It is noteworthy that in the case that outside humidity is higher than the desired indoor humidity level, vent and heat will be ineffective. An automated system might run continuously, wasting great amounts of energy. The third and final factor affecting the cost of vent and heat is the humidity set point. A higher, more relaxed set point will not require as much venting and therefore costs less to maintain. A lower, more strict humidity set point will require more venting to achieve and therefore cost more to maintain. For example, according to Adams, relaxing humidity control from 85 to 90% can reduce energy use by around 12%. We will now discuss 3 alternative methods of dehumidification. The reason for a discussion of alternative dehumidification methods is these alternatives have the potential for cost savings. The addition of a heat exchanger to a conventional vent and heat operation. The use of mechanical dehumidifiers, and the use of chemical dehumidifiers. An air-to-air heat exchanger can be added to a vent and heat system to recover some of the heat lost through venting. This method requires the installation of a heat exchanger but uses the existing heaters, vents, and fuel. Dehumidifiers concluded that the addition of a heat exchanger to a vent and heat operation would lower energy consumption in direct proportion to the efficiency of the exchanger. Heat exchangers used in agriculture are typically 40% efficient. Let's look at a cost example based on the above information. Vent and heat dehumidification is costing an operation 20% of the total energy bill. Heat exchangers are installed to recover waste heat. These exchangers are 40% efficient. 40% of 20% is 8%. So, the operation would save 8% of the total energy bill with the installation of heat exchangers. The research is fairly consistent. Studies by Campen, Dehumidifiers, and Rouse showed that the addition of a heat exchanger to a vent and heat operation can yield a 5 to 17% savings on the total energy bill. For context, these studies took place at latitudes between 45 degrees north and 53 degrees north during heating seasons. Savings will increase when outdoor humidity is high and temperatures are cold. Savings will decrease with low outdoor humidity and in warmer climates where there is less heating required following venting. A study by Gao indicated that in summer conditions as far as 53 degrees north, the advantage of a heat exchanger disappears completely and becomes less efficient than a conventional vent and heat operation. Before installing a heat exchanger, the air exchange capacity of the exchanger must be considered. It was noted by Dehumidifiers and Rouse that air exchange rates equal to or less than 1.2 air exchanges per hour were insufficient. Rouse found that humidity maxed at 91% while the outside temperature and relative humidity averaged 7 degrees Celsius and 61%. Dehumidifiers found that VPD dropped as low as 0.3 kilopascals, while outside temperature and relative humidity averaged 2.3 degrees Celsius and 73.8%. Rouse estimated that 2 to 5 air exchanges per hour might be necessary to maintain a more strict relative humidity set point of 75% during critical dehumidification periods. In a simulation by Dehumidifiers, a proportional control allowing a maximum of 10 air exchanges per hour was able to maintain a VPD above 0.5 kilopascals. Finding an exchanger with an appropriately high flow will depend on the greenhouse's internal volume. To achieve a high flow rate, it may be necessary to install several heat exchangers. Although these studies estimate a payback period between 3 and 9 years, payback will depend on outside conditions throughout the year and internal set points. Keep in mind that the studies here took place at latitudes between 45 degrees north and 47 degrees north. We will now move to our second alternative, the mechanical dehumidifier. The mechanical dehumidifier works by creating a cold condensing surface. This may be accomplished by using a heat pump to separate greenhouse air into warm and cold, with the cold air being used to create the condensing surface. This may also be accomplished by using a refrigeration system. A mechanical dehumidifier saves energy by recycling warm greenhouse air rather than venting it and replacing it with cold air from outside. In addition, water releases heat when changed from a gas to a liquid. This heat stored in water vapor is known as latent heat. The latent heat energy released from the water vapor as it condenses back to a lower energy liquid, as well as the heat produced by the operation of the dehumidifier, can be used to supplement greenhouse heating. Research on mechanical dehumidifier use in the greenhouse is not as comprehensive as research on heat exchangers. Near 48 degrees north latitude in spring season, Migeon maintained a 2,350 square meter greenhouse at 92% humidity or 0.1 kilopascals VPD with a heat pump dehumidifier employing 2 electrically driven refrigeration cycles. This device was reported capable of removing 32 liters of water per hour. Not including latent heat release, this system reported between 72 and 79% energy savings when compared to a comparable vent and heat operation. Latent heat recovery is a significant advantage of mechanical dehumidifiers. Gao reported that when latent heat was taken into account, a household dehumidifier was capable of introducing more heat energy into the greenhouse than the electrical energy it used. When latent heat is not considered, Migeon reported 72 to 79% savings in comparison between use of a mechanical dehumidifier and a conventional vent and heat operation. When latent heat is considered, Gao reported 188 to 203% savings in comparison between the use of a mechanical dehumidifier and a conventional vent and heat operation. An additional advantage of a mechanical dehumidifier is that water recovery and conservation is possible. One final advantage is the greenhouse can be a closed operation. A closed operation reduces pest entry and conserves supplemented CO2. As with a heat exchanger, the advantage of the mechanical dehumidifier is dependent on the conditions surrounding the greenhouse. As outdoor humidity lowers, the mechanical dehumidifier loses its advantage, and may lose its advantage completely in a warm environment where excess heat from condensation of water vapor is unwanted. We will now move to our third and final alternative, the chemical dehumidifier. A chemical desiccant can be used to absorb moisture from a greenhouse environment. A commercially available example is the ventilated latent heat converter, or VLHC, by Ogum. This unit is intended for use in a greenhouse. This dehumidifier uses a hygroscopic salt solution to dehumidify greenhouses and provide latent heat energy that supplements the heating requirements. Longo tested this chemical dehumidifier and reported a savings of 9.6% when compared to a conventional vent and heat operation. Over the course of the comparison, outside conditions averaged 45 degrees Fahrenheit and 87% relative humidity. Reported savings factor in the latent heat released from the dehumidifier unit. In the study, both the greenhouse containing the chemical dehumidifier and the control greenhouse using a conventional vent and heat operation were set to be maintained at 75% relative humidity. The chemical dehumidifier was able to maintain a 75% relative humidity set point, while the vent and heat operation created internal conditions where humidity was at times too high. Chemical dehumidification has its disadvantages. Conventional humidity control is more efficient than the chemical dehumidification when outside air has low humidity content and is medium to low temperature. In addition, the particular unit studied by Longo requires a boiler for the operation. It is important to keep in mind that all methods of dehumidification will be affected by the amount of plant material in the greenhouse. The more plant material, the more transpiration will occur. Excess water in the greenhouse from overwatering will contribute to humidity in the greenhouse through evaporation. Also, the rate of greenhouse leakage affects the dehumidification processes. All dehumidification methods must be considered in the context of their locations. As outside humidity decreases, alternatives to conventional vent and heat operations lose their advantage. As outside temperature decreases, alternatives to conventional vent and heat operations lose their advantages. Studies considered here took place at higher latitudes in winter season when large amounts of energy are needed to heat incoming air after venting. Lower latitudes will see a reduced benefit from alternatives to vent and heat. Thank you for viewing.